Actually, yeah, actually, I was lying a little bit in the sense that you can do it. So let's say, let's talk first about the tool we use. So this is a general technique called rescaling of kernels. Which tells you, I mean, if you are given a function, let's say delta, on you have an underlying reproducing kernel Hilbert space, H. So H is a reproducing kernel Hilbert space, kernel K, and then you have a function delta on X. The complex function X is the same space where the reproducing kernel is defined. Then you can define a new reproducing kernel Hilbert space H delta, which is the functions of the form. Yeah. Still okay because there was a message from Zoom. Oh, no, it's still running. You can hear me still, right?
Yes.
Okay. With it's that the elements are functions of the form delta times f, where f is a function in H, and simply the norm of delta f in H delta is the norm of f in H. Okay. This is a new reproducing kernel Hilbert space, and you can compute the kernel of this in the following way. So this will have some new kernel k delta. So if I take some g in H delta, g will be of the form delta times f. Right? And what I say is that g of x must be the inner product of g times the kernel at x, the kernel delta, in the inner product H delta. Okay. This is as I defined the norm and hence the inner product. This is just the of d divided by delta kx delta divided by delta in the original space. So g was delta times f. So delta x times f of x must be equal to f of f times this function, which now is a function in H. Okay. So you can see from here that in order to have this equality, kx delta must be just delta x times kx. So let's say calculate at some point y, sorry, here should be X bar delta y. Okay, why I made this choice? Again, I know that this thing exists, so I just have to guess which is the right choice. You see, if I put this function there, then dividing by delta, I cancel this part. So I'm taking the inner product of f times kx in x, and this is a constant which comes out. And taking the inner product of k x with f gives me f of x. So let me write what I said. So if I choose kx delta in this way, then this is equal to f delta x bar k x in x. Okay, because I divide by that, so this goes away. But this is exactly equal to delta x times f. Okay. So this is the reproducing kernel of the new space I defined. Okay. So is this one kx delta is so the point is that if delta is a non-vanishing function, then the zero sets of h delta and the zero sets of h of functions in h are the same. Because if a function here vanishes at some point, if and only if the same function divided by delta vanishes at the same point. So I can, as the problem of zeros is concerned, I can rescale my kernel in this way, choosing any delta I want, and consider this problem of zeros in the new space H delta. Okay. So here I make an assumption that I didn't make yesterday. So suppose that I have a kernel x, y, so that at some point it does not vanish. Okay, I need to make this assumption. So yeah, this I can do this scaling if I have this assumption that at some point my kernel does not vanish. Which if it happens, now I don't really know how to do it, but maybe you can do it even if it vanishes. I don't know. Anyhow, if you have this assumption, then you can rescale your kernel at this point in the following way. You choose delta. Let's see what is the right. So yes, delta n. You choose it to be the square root of a x 0 x 0 divided by a. Okay. And with this choice of delta, then the new reproducing kernel is delta bar of x. So square root of a 0 0 bar. Then we have k x y, and then you have delta y without the bar. Yes, this is the new kernel. Okay. And at the point x0, this kernel becomes at the point x0, this kernel becomes this kernel, which simplifies and gives me, so this square root will give me a k of x0, x0 without square root. Here the bar does not play wrong because this is a positive number now. And this will simplify that. Okay. So now I rescale my kernel so that at the point x0, the new kernel is just constant 1. And as I discussed before, the 0 sets are the same for the old and the new reproduction kernel Hilbert space, so it does not really make any difference. And I use this assumption. I will have to think about this assumption.
That's Pellegrino space. That's not what.
No, yeah, for Pellegrino space, all this, okay, we don't have any multipliers, so all this does not make any sense. But I will have to think if you, because there are some spaces where you have zeros and you have also multipliers, like space of the annual, so it's not. But anyway, I will have to think about that. Okay. So this is apart from this this trick, I used it for this 0 sets. This rescaling of the kernel is an important operation in the sense that it leaves also invariant completely the multiplier algebra of the space. So. So note that so the multipliers of the rescaled space are equal in an isometric way with the multipliers of the original space. That is because if I take phi, if I take a function phi, and I want to calculate the multiplier norm, let's say in this space, so that will be the sup of f phi times g in its delta for all g in its delta with norm less than 1. Okay. But g in its delta are functions of the form delta times f, and the norm is the norm of f. So this is the same as taking the sup over all f in eighths of norm less than 1 of phi times delta times g in its delta. But the norm in h delta is that the same the norm of the function divided by delta in h. So this is which is exactly the multiplier norm of phi in h. So that thing, which was the multiplier norm of phi in h delta, is the multiplier norm of phi in h. So this operation of rescaling, it changes the Hilbert space on the level of the Hilbert space, but it leaves the multiplier algebra invariant. So that is the reason. Now I might Okay, that is the reason that the hard space on the upper half space and the disk are not conformally equal. I mean, you don't take the one by composing with the conformal map the other, but the multiplier algebras are the same. Okay, that was a common outside of the question. Okay. And okay, yesterday we discussed
Okay, interesting excellent. So,
yeah, the index extent module that I did not define the hard space in the upper half space. And conformal.
well, that's it, that's part of it.
So yesterday we discussed the abstract peak problem, and we saw that we have the necessity of the condition of the positivity of the matrix always, and when we have also the sufficiency, we call this space is peak space. Today we will discuss an interpolation problem and the sampling problem, which are closer to the Shannon sampling theory. Okay. So in particular, Shannon sampling theorem will be an instance of this interpolation problem that we will define abstractly. And we will go from there. Okay. So let me recall you the sounds sampling theory. So again, we had this space called the Pali-Wiener space of functions in L2 of R with Fourier transform supported in minus a over 2. And if you define these vectors in the space k kn of x to be a times the sink of p a n minus x minus n for me. Yes. We had that a function f in Pali-Wiener can be written and an infinite series right, of samples of the function at the integer times times the sink or in a different way. So these are all things that Nicole already discussed. Or in a different way, this is exactly the inner product of f with k n normalized times k n of x. And the convergence was in L2 and uniform. And from this, Nicola proved actually that k the normalized that Kn is an orthonormal basis for the space. Kn. And this is the general idea that we will try to pursue, that interpolation or sampling sequences, interpolation or sampling properties of sequences can be somehow reflected to base properties of kernel, normalized kernel vectors. So this is now having an orthonormal basis is really the best of the best worlds. Okay, so we will to define sampling and interpolation more generally. We have to be a bit more relaxed to our conditions. So instead of an orthonormal basis, we have. I mean, orthonormal basis is a system of vectors where the Pythagorean theorem is true and where the Parseval formula is true also. So we try to relax a bit these definitions. So suppose we are in a for now you can assume that H is just an abstract Hilbert space, not really a reproduced Hilbert space. And you have some vectors G and some sequence of vectors in X. So if we weaken the assumption of the Pythagorean theorem, we get an almost Pythagorean theorem, which tells you that maybe you fail to have exact equality by some point. Sorry. Pythagorean theorem will tell us that this is exactly equal to this sum of the L2 norm of this sequence again. Okay, so what I ask is to have an almost Pythagorean theorem. So I ask to control this norm from above and below. So here, not bother to define these infinite things. I will ask this to hold for all an which are eventually zero. And with constants, absolute constants n. This is if this almost Pythagorean theorem holds, we say that the Gn is a Riesz system. I would like a name for this definition, which would remind more of this geometric property. And the second possibility is that I have an almost Parseval formula. Parseval formula tells me that if I calculate this, for any vector in the space, I get exactly the norm of X. So an almost Parseval formula is that I get the norm of X bounded below and above by a constant. If this holds for all X in the Hilbert space, if I have this almost Parseval, I say that Gn is a frame. So these are two definitions which somehow relax the conditions of an orthonormal basis. By the way, so let's put here one thing. If a Riesz system is also complete, so if it spans the whole space, it's called the Riesz space. So if
Sorry, Nikos, what is C infinity with infinity?
0, 0. It's all eventually 0, 0.
0, 0. Okay, thanks.
So not just to avoid to define this infinite, the convergence of this infinite. Which if it holds for all C 0, 0, it will converge for all A, N, and 2. But we don't have to prove it.
Thanks.
Yes, if any system is complete, is called okay. And I would say that these are two very natural, two natural conditions. The idea is to go abstractly again and say, okay, if I have a sequence of points, okay, I consider the corresponding sequence of normalized kernel vectors. So I get inspiration from polylinears from some sampling theory. And if one condition is satisfied, I call it somehow, the other condition is satisfied, I call it something else. So that is what the actual definition looks like. Now, which is the reproducing kernel Hilbert space? And Zn is a sequence of points in X. Right? I consider Gn to be the normalized kernel vector. KZn. The kernel vector of the point Zn. If Gn is a Rift system, Zn is called 8 interpolating. And if Gn is a frame, I call Gn H sampling. Okay. So this is really motivated by some sampling theory. So why frame is sampling and the risk is interpolating? We will go into that. But at this point, I think the idea is clear. You look from the sequence, you pass to the kernel vectors, and you ask some base-like properties on the kernel vectors to define sampling or interpolation. So it's easier to see why why we call in the when Gn is a frame, why we call that n sampling. So what happens? Let's apply the definition of frame to Gn. Okay. Frame means that I have a constant A and B such that for any function f in the reproducing kernel Hilbert space, I have that the norm of f is bounded by the inner product, absolute value, the inner product of m with Gn. This is bounded by again the normal function. But what is this? This is the inner product of f with the kernel vector. divided by the norm of the kernel vector. Okay, so this is exactly that. So sampling means that by sampling the values of the function at the points Zn and calculating this weighted L2 norm, I can recover more or less the norm of the function in the space. And that's why we call this sampling. Yes. In particular, for example, if f vanishes or on these points, then f must be the zero function. This is the stable version of saying that if f vanishes at n, then f is the zero function. So that this is pretty clear. A bit more intricate is why where interpolation comes in one, and we need some amount of functional analysis to see that. Let's do that. So the definition of three system was that so the three system by definition that we have this inequality. It's called A. Which we can translate in functional analysis language by saying that this operator T, which starts from L2 and goes into H and maps AN to AN GN, is a bounded linear operator, which is bounded above and bounded below, no? Because this is the risk system requirement is just saying that T applied to some sequence AN in X is bounded. Here I will use a lemma from functional analysis, which I will prove after I finish this this part. That's because it will just lead us off track now. So I will use the following lemma. So if you have an operator T from one Hilbert space to another, T is bounded above and below, depending on if the adjoint is subject. Of course, bounded and subject. Okay. I will prove it after I apply it to this case. Okay, so yeah, of course, we have to compute the adjoint to see what this gives us. So computing the adjoint of T, T star is an operator now from A going into L2 of N. Which, if I apply it to some F, and then I pair it to some sequence, as an example, 2, this by definition should be F paired with T applied to the sequence. In H9, but T applied to the sequence was just AN GN. This thing converges in norm, so I can pull the sum out. And we have here A and bar F F paired with Zn, which we computed also before, that F computed at Zn divided by the norm of the Kelvin vector. But this is equal to that, okay, which means that if these things are the same, then T star of F must be exactly this quantity over there. T star of F is exactly a sequence which is given by F restricted to the then normalized. So the adjoint of T is just a restriction operation. So saying, by applying the lemma, saying that T is bounded above and below means that the adjoint is subjective and bounded. So Zn is interpolating if and only if T is bounded above and below by definition, if and only if T star is subjective by the lemma, if and only if subjective, just I write down exactly what subjectivity means. It means that for every L2 sequence, I can find the function f in H such that f of Zn divided by the norm of the kernel vector is equal to An. And T star has to be bounded also, so it means two things: this interpolation condition and I don't have enough space. And that right. It means two things. That for every sequence in little 2, I can find f in H such that f of Zn is equal to An norm of the kernel vector, and that this operator is bounded from H to L2, which means that I have this inequality. Okay. So this is why this is exactly why we gave this definition of interpolation, because in fact, asking the kernel vectors, the normalized kernel vectors, to be a Lie system is equivalent to an interpolation problem plus some boundedness of the some control. Yeah.
Why the last inequality is
The last inequality is just rewriting what it means for the P star to be a bounded operator.
okay, so there is a constant.
There is a constant.
Okay, I can okay.
For some constant, so there exists a constant C, so that this holds for all. Okay, maybe I can even give a proof of this lemma from functional analysis, which they use without. Okay. Yes, so I wanted to prove this, but this is my worst proofs because it's a bunch of tautologies together that I always lose track of. Okay, so if yesterday night I was correct, so so suppose that E is subjective also. So as I said, so if T is subjective, then it means that T is just a Hilbert space isomorphism. Okay, it's a bounded invertible. So T then this implies that T is bijective. It's bijective because it's bounded below and it's subjective and it's continuous. So it has a continuous. It's a continuous bounded integral. It's a bounded linear integral. Okay. In this case, this thing is trivial because then also T star is invertible because T star multiplied to T minus 1 star is the identity, and also T minus the identity. So T star has also an inverse. So also T star is a Hilbert space isomorphism, so in particular it has to be subjective. Okay. So this is trivial to the things. I if is trivial space. So, and also in this case you can also go backwards, right? because if T is a filter space isomorphism, and T star is then T star also is yeah, T star is subjective if and only then this is always the case.
If T star.
So let's say if T is on, then if this holds, then this holds.
All right,
If T star is subjective, yeah, if T star, sorry, if T star is subjective, yes, we are still in the first case where we suppose that T is subjective. Then the kernel of T is the range orthogonal. So now if T star is subjective, then T is injective because this is 0, and then T is injective and subjective, so it's bounded and bounded above and below. So this implies that T is injective, which by assumption it was also subjective, so T is bijective. So this implies that T is bounded above and below. And the idea that the general case is not so different because, so now suppose that T is not subjective. So suppose that we are in the general case, okay. So T is bounded. So the hypothesis, so proving this, the hypothesis implies that the range of T is closed. So I can find a projection P from K to the range T, a bounded linear projection. But then this means that T is subjective and bounded above and below. So I can apply the first case. So this implies that if I take the star, the operator is subjective. So by the case 1, this is subjective. But if I have a composition of two operators which is subjective, then the last one has to be subjective. Okay. And the other way, suppose now that T star is subjective. Then I take, so this star goes from K to X. Okay. I can decompose K as the orthogonal sum of the closure of the range of T. So I don't know yet if T is it has closed range at this point. So I take the closure plus the orthogonal complement of the closure of the range. But the orthogonal complement of the closure is just the kernel of T star. And if this, okay, so now take a projection on there. Take another projection P, I don't know, from K to the closure of the range P. So if T star is surjective, then it must be also if I compose it with P bar. Because this just kills all the vectors that are in the kernel of this star. So if it is surjective, it must be surjective just restricted on this subspace because all this goes to 0. But this is surjective and it is injective because I killed the kernel. So we can apply again case 1. So the adjoints must be bounded above and below. But this is just the operator P, because P star is the orthogonal projection, so the star is not doing anything, and P bar is projecting on the range of T, so it lives invariant T. So T must be bounded above it. So I think that's pretty much how you prove it. I don't know if there is a, okay. Okay, let's make a break. Okay.
It's used to also for more general analysis.
The recording is still on.
Oh.
Oh.
Thanks, Davide. Okay. On a lighter theme, let me tell you that, for example, hard disk space does not have any sampling sequences. So imagine you have a sampling sequence for the hard disk space. Take A. Sorry. It would mean that you have an A positive for which the norm of any function in the hard disk space is bounded by the samples of the function at some point times the 1 over the norm of the kernel squared, which is exactly this quantity. And you can also control this above, but this is enough to arrive at a contradiction. So imagine I put f equal to f capital N equal to z to the n. Then the norm of f is just 1 because it is the L2 sum of the coefficients of the function. So I would, this means that I have an absolute constant A which bounds below this infinite sum. For any n, and A is dependent on n. But then by monotone convergence theorem, I can take the limits as n goes to infinity. All these z n are points inside the open unit disk, so this tends to 0. And so I have a contradiction. Even though Palevina has something, at least one sampling sequence, integers in particular, Hardy space does not have. So it's general, but we will see that. So in the presence of this peak property, that's the last topic for today, that we will see that in the presence of peak property, interpolation, as we defined it today, is equivalent to interpolation in the sense of Carlson, so in the sense of Carlson's interpolation theory. So first, let me define what is the abstract Carlson interpolation problem. So sometimes called also multiplier interpolation problem. It is the following, since we saw peaks, after peaks problem, it's very natural to generalize also Carlson's interpolation problem, because Carlson said that, so for which sequences that end is the restriction operator so going from A to infinity to L infinity subject. And of course, now that we know that H infinity is a multiplier algebra of H2, it makes sense to ask for if you have a reproducing kernel Hilbert space H, for which that n in the domain X is the operator going from the multiplier algebra of H to L infinity. So sorry, here I didn't define the operator, but the description operator. is again the restriction operator bounded, subjective. This is the abstract multiplier interpolation problem of Carlson's interpolation problem. Note that as in the H infinity case, this operator is a linear operator and the contraction because of what we proved today, yesterday, that if I take R applies to some phi, and I take the L infinity norm, this is that the soup over all possible n, the n, which is less or equal than the soup of phi everywhere. But we saw that the supreme of phi is less or equal than the multiplier norm of phi. Okay, so this is a linear, this is a contraction. Okay, it's always well-defined, bounded, and the problem is to characterize the sequences Zn for which this operator is subjective. So, which means that I can solve the interpolation problem for L infinity data by a multiplier in H. Okay. And we will see that in the presence of the peak property, this is equivalent to the interpolation problem in the Hilbert space itself that we defined before. Okay, this is the main theory. So if X is a resolution kernel Hilbert space with the peak property, then the following are equivalent. One, my sequence is 8 interpolating. This means that this corresponding system of normalized kernel vectors is a RISC system for the conditions of the restriction operator on the Hilbert space we defined before. Two, Z and 8 is multiplier interpolating. Okay. For example, as a corollary, since for H infinity we know the interpolating sequences by the theorem of Carlson, we know automatically also the interpolating sequences for the Hardy space H2. So corollary, Zn in the disk satisfies Carlson condition. Which holds if and only if I have interpolation in H2, which means that for every sequence in H2, I can find a function f in H2 that is that f of Zn is equal to a n then n squared to the 1 half. And I have the boundness, the second condition of the boundness. Okay, this is the corollary of this theorem that we will prove, and Carlson interpolation theorem for H infinity. So automatically we get for free an interpolation result for the Hilbert space if we have an interpolation result for the multiplier algebra for peak spaces. Okay, here we used also the fact we used, if we want to be precise, we used 3 theorems. We used Peake's theorem in interpolation that we proved some time ago. We used this theorem and we used Carlson interpolation theorem to get this results.
Why the last inequality?
So interpolation it means that the adjoint of this so it's at some point I wrote that interpolation means that this operator is subjective, this restriction operator is subjective and bounded. Okay.
Okay.
So I have to assume the boundness and the subjectivity of this restriction operator, which is exactly this. I don't want to go very much off track, but you can prove separately of this that this is redundant for the Hardy space. So you can remove
Okay.
but it's not, we do not get it for free from what we know. Okay, so this is going we cannot prove it right now. But yes, for the Hardy space, and only for the Hardy space, in fact, you can prove that this second condition is redundant. You get the equivalence even without assuming the second condition. But this is not included in what we know. So proving this theorem, let's go from 2 to 1. So I will be so I will leave a small asterisk in the proof that I will compensate in the ones that some limiting argument that I think I would prefer to skip. But anyhow, the main idea of the proof is the following. Okay, interpolation means so from 2 to 1. From 2 to 1. Multiplier going to Hilbert space. So let me first do one. So I know that my sequence is interpolating for the Hilbert space, and I want to prove that it's interpolating for the multiplier algebra. So what I know is that I have this inequality. For some function A, the sum constant B, and where Gn is just the sequence we have the vectors normalized. And I want to prove that given some Wn in N infinity with norm sufficiently small, I can find a multiplier. So I can find a multiplier in the multiplier algebra. The phi of Gn is Wn. I can, in fact, make this quantitatively. I can prove that if the norm, the modulus Wn is smaller than A divided by B, I can find a multiplier with such a relation problem. And of course, I want to construct a multiplier. So I use the only thing I have, which is the peak property, which tells me if you want to construct a multiplier, you have to check the positivity of some matrix. Okay. So I truncate my problem because peak property is defined from finitely many points. So I take Z1, Zn, and W1, W capital N. And I want to solve this interpolation problem. Find multiplier P, which sends Z1 to W1, Zn to Wn. And I know that I can do that if this thing is positive for every choice of scalars. I can know, so if this is always positive for every sequence of scalars, this multiplier exists. So for every, sorry. So what did I say? For every sequence of data in infinity with norm less than A of B, I can find a phi, yeah, which even has a multiplier of 1. Okay. By scaling for any sequence of N infinity data, I can find some multiplier which interpolates.
Sorry, why it exists, this phi?
No, I didn't prove it yet. So what I say is that by Peake's property, it suffices to check the positivity of this quadratic form.
Okay, thanks.
This is plain. So let me rewrite things a bit. So here I can, so I know some things about the Gn. So let me, first, I can write the kernel of that at Zn calculated at Zn. I can write it as K of Zn, scalar K of Zn. And if I want to create this vector Gn, I should normalize. And then I came back. Okay. But now I can somehow absorb these two things into the scalars. Because yeah. Okay, and this is positive for all choices of Tn and Tn, if and only if the same thing without normalizing, because I can just define some T prime, which is Tn over the norm of K Z n. Okay, so it really, this is equivalent to say that I have positivity for all Tn and Tn of this thing.
Sorry, why in the scalar product Gn is before Gm?
Yes, so I forgot things here. This is bar, I guess. And
What we were at Kz, the M of Zn, so it's Kzm scalar Kzn. Kzn.
yes, so this
Right.
and here.
Am I right? And
Now it's
should
correct.
be, ah, seems better. Yeah.
Now it's correct.
Is that okay?
I think so, yes.
Yeah, because from here I cannot see the products so bad, so good. So
Yeah, it's first M and then N.
okay.
Yeah. Okay. So this is equal to I split, I multiply out these values here. So this is E and T and times T and bar T and T and bar. So let me just for convenience, let me put the bar here. It's the same thing, right? Because I can, if it holds for all scales, it holds for the conjugates for stars, so that I don't have to carry this bars everywhere. So this is the first part. If I multiply here, and I subtract the second part, which is the same with the Wm as well. Here.
Maybe here you have the bars. On the W's.
On the W, yes, here I have it. Okay.
Not a problem.
Yeah. So I put the sum inside the scalar product, so it becomes the sum over all n T and T n against the sum over all n of T n T n. Okay. by linearity of the scalar product. The same happens in the second part.
Sorry, Nikos, the second part is the sum from 1 to infinity to what? I don't see what.
From 1 to n capital N. So it's the same thing, only that I have a WN bar in the first part and a WN bar on the second.
Thanks.
The N, W, N, and the same here. Sorry. So again, if you don't see from the web camera, it's the same. It's the same. Just you have also the W bars appearing. Okay.
Okay.
But this is, of course, just the norm of this vector square. And here I have the norm of the same vector with different coefficients. And here I use the inequality that I know. From interpolation. So I know that this is bigger than A times the sum of the squares of the coefficients. So this is bigger than A times N squared. And with this, with the minus, is bigger than minus B times, again, the sum of the squares of the coefficients. Okay. And here I use the fact that my Wn has small norm, in fact, that's A over B. So in the end, I will get that this is greater or equal than A times that thing minus B A, sorry, I mean the square root. So that I get really A divided by B. Okay, this is 0. So I proved that the peak matrix is positive. And this implies that there exists a multiplier of norm at most 1, which solves this interpolation problem. So there exists some multiplier phi n norm less than 1. So the part that I will skip now is that you can do a limiting argument. I mean, it's very intuitive that since the condition does not depend on capital N, and since the multiplier norms are uniformly bounded by 1, I can take some kind of limit point of the sequence, which will solve the entire interpolation problem for infinite points. But I don't want to become too technical, so this implies that there exists a multiplier norm most 1 which solves for interpolation. I mean, the argument involves, it's just an application of the Banach-Alaoglu theorem, but you need to know that you need to know that the multiplier algebra is a dual space, so that you have,
Oh,
a weak start topology, where you can apply Banach-Alaoglu. But
yeah.
you need to show that it's a dual space, so then where you have to do some functional analysis, but it's not really easy to do. And the other part of the proof, so the other part of the proof is to show that if it's multiplier interpolating, then it is also interpolating for the Hilbert space itself.
The other part does not.
And it does not use the peak property. And the other part is then. So now I'm going from. It is the theorem. So from 2 to 1. So and so the idea is that you choose. So this, you choose these target values in L infinity. E to the 2 pi t times j.
So what is the name? In the left is W, J.
What is Wj? Is 2
Yeah,
pi.
I cannot read it very well because of the blackboard.
So it's just the element of the exponential basis is e to the 2 pi j times t. That's W and j. Which depends on the parameter t, right?
Okay.
So I don't write it, but it depends also on t. Then
I is the complex. Yeah.
I is the complex unit. Then there exists a function, a multiplier which depends on t. Which has norm multiplier norm less than a constant times the subnorm of Wj, which is some constant. This is 1 because these are all modular numbers, such that t of zj, let's say, in Wj. And then this is the way we use the interpolate Su property. And then we do again the same trick that we did yesterday. We pass to the adjoint. In the sense, we define some multiplier operator from X to 8. But we prefer to look at its adjoint. and saying that its adjoint has norm less than t, it's equivalent to say that inequality is satisfied. For all F equals. And then again, the same idea, you just look at functions f, which are linear combination of the kernel vectors. So some an, bn, where, okay, to be safe, we take an to be a sequence which is eventually zero. This is very similar to the computation we did yesterday. Right? So from yes, from one hand we have that the norm of f is, so now I write it in one line because we did the same yesterday, is an bar, to infinity. And again, I write on one line this computation because it is exactly the computation yesterday. Going to be an. I get also the eigen values of this operator, which are the wj or wns. So I e to the 2 p n times f. We can here. Again, g and okay. Yes. That is okay. Let's we did it yesterday. Let's see. Because if you apply this operator to f, you get a and applied to in the n divided by this one. And the important fact that we used is that the kernel vectors are eigenvectors of the adjoint multiplication operator. So this will give us p at n bar times k. Okay. But this was exactly wn. So this is exactly e to the 2 I and e with the minus because we have the column. Okay. And then again you take the norm of this thing squared by these things. And so rewriting what this inequality means for this coefficient of f. So now this inequality becomes a bar e to the minus E and minus n. In here. Let's record on. Infinity here, but and now I integrate both sides with respect to t. So I remember these are finite sequences, so I can do that. And if I integrate, here I have it. If I integrate the left-hand side, I just get the diagonal terms because all the others give me 0 from the exponential. Here I get again. Okay, which is exactly the left-hand side of the risk system condition. Is the left inequality of the risk system condition. Okay. And then it's already 11, but it's completely symmetric, if you believe me, to get the right inequality just by now putting an. So we are free to choose an as we like, and C is independent of an. To prove the right inequality, you just put an to be equal to e to the 2i n times some other an tilde, and you will get inequality where you will have the exponentials of the right hand side, and by integrating you will get also the right inequality for the risk system condition. And this proves that you have the risk system condition and hence the sequence is interpolated. Explanation.
Sorry, Nikos, how do you prove the corollary about Carlson interpolation?